In a quiet unveiling in Shanghai, China just showed off a 250-ton mining truck that can walk sideways like a crab with nobody behind the wheel because there is no wheel to sit behind. Traditional haul trucks operate on the same mechanical principles as standard passenger cars. They steer by pivoting their front wheels, forcing the entire massive frame to follow a wide sweeping arc. On open highways, this layout is highly efficient, but inside the cramped confines of an open pit mine, it creates immediate structural challenges. The scale of these machines makes every turn a high stakes calculation. A fully loaded conventional haul truck can weigh as much as 200 consumer pickup trucks combined. Maneuvering this massive concentration of weight on steep, irregular slopes of loose gravel and clay requires immense physical space, as the wheels must claw for traction while the chassis fights gravity on narrow, unpaved ramps. When these giants reach the bottom of a pit to receive a payload, the space constraints become acute. Tight loading zones do not offer the wide turning circles these vehicles require. Instead, drivers must perform slow, multi-point turns to align the truck bed with the excavator, a process resembling parallel parking on an industrial scale. This constant back and forth repositioning on uneven terrain accelerates mechanical wear on the tires, steering linkages, and hydraulic suspension components. Because these systems rely on a single centralized pivot point, any steering adjustment under full load puts immense torsional stress on the front axle. Every second spent backing up and adjusting the truck's angle slows down the entire mining operation, while the massive blind spots inherent in traditional cab designs increase the risk of ground collisions. As pits go deeper and haul roads narrow, the limits of conventional steering geometry are reached. In an open pit mine, blind spots are permanent structural hazards. When a haul truck driver turns the steering wheel, the massive hood and elevated cab block the view of the surrounding ground, creating blind zones where smaller support vehicles and ground workers completely disappear. Because loading areas are tightly congested, even minor steering adjustments under load can result in fatal collisions. The human cost of these physical limitations is documented in historical industrial safety records. Systematic data from Chinese mining operations between 2004 and 2015 reveals the scale of this hazard, recording 20,731 accidents and 34,729 deaths. A high percentage of these incidents occurred during low-speed maneuvers in tight loading zones, where operators simply could not see the immediate path of their tires. These figures prove that safety in heavy mining cannot rely solely on operator vigilance or auxiliary warning sensors. The core problem is the basic geometry of the vehicle itself. When a massive machine must swing its entire frame to change direction, its blind spots shift and expand dynamically, sweeping across the working area. This hazard increases in deep pits where haul roads narrow and vertical rock walls restrict sightlines even further. Under these conditions, traditional steering mechanics force a constant dangerous compromise between productivity and human lives. The safety pressure within these environments demands a vehicle behavior that eliminates the need to swing the chassis altogether. On April 18, 2026 in Shanghai, the Shuanglin Group and Tsinghua University unveiled the Shuanglin K7, a machine designed to bypass traditional steering mechanics entirely. This vehicle has an empty weight of roughly 100 tons, yet it carries a payload of 158 tons, bringing its maximum gross weight to nearly 250 tons. Physically, it is a giant, measuring 13.79 meters long, 5.7 meters wide, and 5.2 meters tall. Despite this scale, the K7 possesses an agile locomotion set that defies typical automotive design. Unlike conventional trucks, it can glide diagonally across the ground, translate directly sideways, and perform a full 360-degree rotation on the spot without changing the direction its chassis is facing. By decoupling the direction of the wheels from the orientation of the vehicle frame, this design allows a 250-ton machine to negotiate tight spaces and travel down narrow haul roads with absolute precision, removing the physical necessity of making sweeping turns in cramped, high-risk mining zones. Traditional haul trucks rely on rigid steel axles that mechanically tie the left and right wheels together. When steering, a complex system of hydraulic cylinders and metal linkages forces the front wheels to pivot together, while the rear wheels remain locked in a fixed path. This machine completely dismantles that architecture. It eliminates centralized axles, mechanical steering columns, and pneumatic brake lines, replacing them with 4 independent self-contained corner modules. Inside each wheel hub sits a dedicated permanent magnet synchronous motor, a high-precision steer-by-wire actuator, and an electronic braking unit. Instead of relying on physical connections, these modules communicate via a high-speed electronic backbone. This distributed drive-by-wire system allows the control software to command each wheel separately, continuously adjusting torque, wheel angle, and braking pressure. Without the physical constraints of a shared axle, the truck no longer needs to pivot its frame as a single rigid unit to change direction. Instead, the vehicle's overall movement is calculated dynamically, composed wheel by wheel, translating digital inputs directly into precise, non-pivot locomotion. Operating without a driver cab, the K7 is designed for Level 4 autonomy, meaning zero human intervention within its mapped operational boundaries. If a system failure occurs, the manufacturer claims the truck can maintain 70% of its operating capacity. For an industry built on strict margins, verifying these claims requires more than promotional videos. Engineers demand time-stamped telemetry logs detailing real-time wheel torque, steering angles, brake pressure, and battery state of charge. Independent safety audits and controlled failure tests must confirm how the software handles sensor dropouts and thermal spikes. To establish real-world viability, operators also require documented evidence of loaded range, cold weather behavior, and the long-term logistics of maintaining specialized corner modules in remote, dust-choked environments. China has established a national mandate to fully automate its entire mining sector by 2030. This shift is already visible across the country's resource-rich regions. In the harsh expanses of the Gobi Desert and the sub-zero coal fields of Inner Mongolia, hundreds of autonomous heavy trucks now operate around the clock, and some pilot sites are already nearing 90% fleet electrification. Yet, standard driverless haulers still rely on traditional steering geometry, which restricts their use to wide, predictable haul roads. The K7 is engineered to operate where these early autonomous vehicles struggle. It is designed specifically to conquer the tightest, steepest, and most irregular pits, geographical zones where space constraints prevent traditional machines from safely turning, loading, or maneuvering. By removing the need to pivot, vehicles like the K7 alter the physical design of the mine itself. Traditional open-pit layouts allocate significant real estate for wide turnarounds at loading zones and dump sites. Eliminating turning radius requirements allows engineers to narrow the benches, freeing up valuable ore-rich ground and shrinking the overall pit footprint. This layout change reduces docking times, improves clearance safety, and compresses cycle times, directly increasing hourly tonnage throughput. Yet, integrating these machines presents complex commercial challenges. Operators must weigh high unit costs against productivity gains while managing workforce retraining. Maintaining 4 independent corner modules increases the maintenance burden, and electrification benefits are tied to the sourcing of rare earth motor materials. Regulatory approval and long-term reliability remain open questions. The K7 proves the future isn't about automating old vehicles, but redesigning them entirely. By abandoning human constraints, this technology is fundamentally restructuring how industrial spaces operate. The machine of tomorrow won't just adapt to our world, we will design the world around it. Thanks for watching.